Thank you very much. It's my pleasure to be here. I've heard a lot about Saturday morning physics over the years. I've had friends that have presented, so I'm feeling very fortunate to get the call to come try to entertain you for an hour. I study human movement, and one of the most purest forms of human movement is running. And so I thought it would be really interesting to talk about the basics of what we know about the physics of running and how that's changed over the years. You can look at the best athletes in the world, whether it's Usain Bolt or Joan Benoit Samuelson, both Olympic champions, marathon runner, sprinter. They have very different body morphologies. They run differently, but in many ways they run very much the same. And there are some basic principles that govern how they run that also govern how you and I run, even though we don't quite move as fast. In my laboratory, we study the biomechanics, the neural control, and the energetics, because all three are very intertwined in determining how we move from point A to point B. If you want to get up in the morning and come to Saturday morning physics, you generally adopt a way to walk or run, depending on how fast you want to get here to get the donuts. In terms of using the least amount of energy, we're really good at figuring out the way to move so that we don't increase our heart rate and to do more work. And in fact, my friend Art Kuo calls this the principle of laziness. We want to get from point A to point B that uses the least amount of energy. And so energetics is a huge component when we talk about just natural everyday behavior. That dictates some of the mechanics, and then the control has to adapt to both of those. However, even though we study human locomotion, I want to make the point we really don't know as much as we'd like to know. And to put this in perspective, I want to take you back to 1997 when IBM built a computer called Deep Blue, which beat Garry Kasparov, the world's greatest chess champion, in a very complicated cognitive task. They played chess. People back in the 50s and 60s thought we'd never be able to get to a computer that could do complex strategy, planning, cognitive tasks like playing chess. But in 1997, which was quite a while ago, we were already building computers that could do these cognitive tasks. So the question is, what's the analog? Can we build a machine that can outperform the world's best human at locomotion, a physical task? And arguably, this is the world's best walking, running robot. So this is Honda's Asimo. If you haven't seen Asimo, they've been working on Asimo for 15, maybe close to 20 years. They've spent tens of millions of dollars. And it's pretty impressive. It's a very good engineering feat. But when you look at how much energy it can store in its backpack, it'll run for all of 60 minutes on close to 4 million joules of energy. And if you put that in kilocalories for you and me, that's 2 Big Macs for an hour. And its top speed is 1.8 meters per second. So that's good compared to where we were 10, 15 years ago, but I'll put it in comparison. I'm not going to compare it to Usain Bolt or Joan Benoit. I'll compare it to my 7-year-old daughter, Logan. And if you look at what Logan can do, for the same 60 minutes, she'll run on 200,000 joules, which is 2 carrots, not 2 Big Macs, if I can get her to eat them. And her top speed is 5 meters per second. And she's actually a lot better at adjusting to things like sandy terrain than Asimo is. There are videos online if you want to find Asimo falling down doing all sorts of things, because it falls quite a lot when it's in structures that it's not used to and it hasn't experienced before. My daughter can do that really easily. She can go to sand or mud, especially mud, and a lot of different things, and do it quite well. And so I would argue that while Honda spent 15 years and tens of millions of dollars to build this machine, I built this machine in 7 years and a whole lot less money. I had a little help from my wife. But we really don't understand human locomotion as well as we'd like to, because if we understood this better, we'd have a better time building this. And really, the controllers are a huge difference between these two. Our nervous system is so adaptive and can do so many variable tasks that we can't get robots to do yet. If we look at the history, what have we learned over the years? If you go way back, Aristotle, Galen, Da Vinci, all had seminal texts that they've written that still exist today on the biomechanics and the physics of human motion. And then in around the 1600s, Borelli is considered by many to be the the father of modern biomechanics because he started actually doing some more detailed mechanical analyses. And here are some of his diagrams that look into the physics of human motion in walking and running. That changed a lot with Etienne Jules Murray in 1885. Very incredible mind. Murray, living in France, was one of the first inventors of motion pictures. And he did it not because he wanted to, make the next great movie and sell and make money. He was actually a scientist. He wanted to understand human motion and animal motion. And so he figured out a way to set up multiple cameras to take these pictures in intervals, set intervals, and be able to study human motion. And he also built a lot of really cool devices, like this portable gait tracker, where you ran around carrying it and it would measure how long your step length was, how much force you're pushing against the ground. So there, this was sort of a renaissance in terms of human biomechanics of running. Here's a little video from his that was put together from the pictures he made. And the thing I want to point out is that it wasn't just taking pictures, it was analyzing it for the physics and the mechanics. It was actually documenting the actual motion patterns and putting quantification on it. And so that's what those lines show. So that was in 1885. The next big change came with personal computers. The minute we had personal computers, we had somebody named Gideon Ariel in the 1970s who really started to apply these personal computers to do the same type of analysis, but to do it with greater power. So let's listen to him. You may recognize another famous face.
That we also took.
All right, let's show some of that film now and some of the system that you used on the computer so we can show just what Dr. Ariel is talking about. Changing from just an eyeball analysis of it to putting it on the computer there that you can see in front. Is that me running?
This is you running, actually in the marathon
Lost all the weight.
Yeah. And basically you see that you're landing on the heel, which is a deficiency because most of the force is transmitted to your body.
So look how slow this is happening.
People that running like that 10, 15 miles, obviously are going to have some problems. So the style of running is very, very important. Here's a composite picture of your leg motion.
So it's nice to be able to slow things down in slow motion to analyze them, but it actually took all day after you collected the data back then to actually get this stick figure animation, which was much faster than Murray's time, but the computers were very, very slow at the time. He actually, because of this, he was working with the U.S. Olympic Training Center to try to help the U.S. athletes out with biomechanical analysis in all sorts of sports. And he made the talk show circuit. He was on David Letterman, he was on Today's Show, he was on all sorts of things because everybody was fascinated by the application of computers to actually study human running. Today, we do the same type of analysis. So here's a runner in a lab with lots of little markers, these balls that reflect to light, that we can track their motion patterns. And we do it very fast. We can do it in real time. So we put a number of cameras like this one up on the wall that film them, and very quickly we can analyze somebody's mechanics. And we turn it into something that looks like this. Again, the stick figures, we can do the quantification, the analysis, figure out their patterns, try to figure out what are the similarities and differences across individuals. When you get to things like the foot, it actually gets really complex. With 26 bones, 33 muscles, tons of ligaments and tendons that are in here, it's one thing to just make it a single rigid rod like Murray and Ariel did, but if you actually want to know how the foot is moving and you want to design a shoe that works with them, you really want to track how all of these individual bones are moving. And a very hot topic right now in the media is barefoot running. There's a lot of runners out there that are starting to go to barefoot running. They say you have proponents that are saying it's better for you. You have traditional running shoes, which came along in the 70s. And then you have something in between where you have shoes that are minimalist. And a lot of times when I talk to the public, they ask me questions about, is it better to run in shoes or is it better to run barefoot? Because people argue for different approaches. And so to try to address this question, I'm going to step back a little bit and talk, before we get to shoes, let's talk about rubberized tracks. So if you've ever been to the University of Michigan track for the track and field team, it's very compliant, it's very elastic, it's rubber. I did the shot put in college, and you can take a 16-pound metal shot and actually dribble it on the track. It will bounce back up to your hand because it's so springy that it will come right back to you. And so when I was in grad school at Berkeley, I was very curious as to how this was really changing people's running mechanics. And it turns out in my academic family history, so not my mom and dad that raised me, but I did my PhD at Berkeley under Claire Farley, and Claire did her PhD at Harvard with Tom McMahon. And Tom McMahon was a giant in the field while he was alive of biomechanics. And if you actually track back the literature, there were some really big findings that Tom McMahon had a while back. And I'm going to start there. 1977, Tom McMahon was asked by the athletic department at Harvard, if you can believe it. They wanted to design a new indoor track. And they wanted to know, how should we do this? What should we do for this track? And Tom had actually never studied running before. He'd done other types of biomechanics, but he hadn't done running. So for him, he thought this was a cool challenge. And he tried to break running down into the most simplest motion he could, because usually that's a good place to start, is if you can simplify, figure out what captures the essence, then you can add on the layers of complexity as you go. And so what he ended up doing was getting wooden tracks in his lab, changing the way they were supported so he could change their stiffness, and he got people to be subjects to stand and basically cross their arms and bounce up and down. So he'd get them to, instead of doing the full running motion where there's an aerial phase and a stance phase, he basically just got them to do this motion. He tried to simplify. In the end, I found out that this was one simplification too many, and I'll tell you later why. But in doing so, he came up with a spring mass model. Springs are ubiquitous in the way we look at human running because of the way we move. We literally bounce off the ground with each step, and I'll go into that with more detail. But this was the first spring mass model that was ever published looking at running mechanics. And he was trying to figure out, well, how do I change the stiffness of this spring, this surface here, to make this motion move better? And he did some really good analysis, and he built different surfaces. And then he collected ground reaction force data. So he put like a fancy bathroom scale underneath the surface. So instead of just measuring how much you're standing on and statically, it will actually measure the force between your foot and the ground in a very millisecond time resolution. And if you look at those ground reaction forces under a compliant springy track versus one under a very stiff track, what you see is that there's a huge difference in this initial peak. That initial peak is your foot slapping the ground. When your foot hits the ground, it's got to slow down, and it does it with an impact. And we get a very large peak on a stiff surface and a very minimal peak on a compliant track. And he was able to make predictions about what should happen, and he took this model and he actually filed a patent. And he said, you know, based on what we know of the human, you can actually put springs on the shoes, which are, you know, Chuck Taylor Converses, which were common at the time, and you should be able to have people run faster. He didn't do much about it. He was an academic. He didn't really want to create a company, but at the time he filed the patent. Later on, it turns out Nike came calling because they found his patent, and they said, you know, we really want to do something similar, but we can't because you've got this patent. We'd love to give you a big bag of money to take this patent off your hands, and we're actually going to do something with it. So when I was in grad school at Berkeley, I heard about this when we were talking to Tom, and it paid off. This was what they wanted the patent for, was Nike Shocks. I don't know if you've ever seen them, but it's a type of running shoe that looks like it has metal coil springs underneath. What it really has is air springs. So inside is just an air pocket, but it's made to look like a spring. And their idea was maybe we could tune this to get it to work. And they haven't totally dominated the market. If you're a runner, you know that not many people actually still run in these things, but they are out there. And so that was just an example of something coming from an athletic department about their running track that eventually ended up as a running shoe design. But later on, Tom kept working at this, trying to figure out what is the constant for human running that we can say is similar for all of us. And what he ended up was changing his model to make it a little simpler so that you just have a point mass that represents the mass of the body, and then you have a linear compression spring that represents the leg. So if you think of a runner at the three phases of hitting the ground, when they first hit the ground, the middle of the stance phase when they're directly over their foot, and then right before they take off. This is the pattern that their center of mass takes. And if you do a spring mass model and actually run it through all the equations, that's very similar. And this model has now proven incredibly effective to helping us understand how human running biomechanics change under different circumstances. And it's also got a big difference between Tom's original model, and that is it's got an aerial phase. So instead of just bouncing in place on the ground, you take off. That's a really important point of human running because it creates hybrid dynamics. That means I can write one set of equations for what happens when you're on the ground, but I have to use a different set of equations when you're in the air. It's just projectile motion when you're in the air. And so that actually changes a lot because in a minute I'm going to show you some springs that don't have hybrid dynamics, and we'll compare those to the way humans run. But he continued to make measurements of what goes on, and if you actually just look at the force in your leg during running, and he puts it in body weights here, versus the displacement of the leg, what happens is during the landing portion here in blue, the force goes up and the displacement, that means the leg gets shorter. So if you think of me running, when I hit the ground, I start off like this and it gets compressed and then I take off again. And so what happens is your leg shortens and then it extends. And so during this shortening and extension, the forces pretty much mirror a Hookean spring. Forces go up as you shorten, then the forces go down as you take off. So this was, again, more validation that maybe this spring mass model could be useful. Some of his students, Roger Crom, worked with Tom McMahon and Jiping He, who was a postdoc, and they actually measured that stiffness of your leg while you're running at different running speeds. So here's the stiffness on the y-axis, and here's your forward speed. We start to run at about 2 meters per second, so this is a slow jog. And then typically most people don't run faster than 6 meters per second when they're out for any type of recreational run. 2 to 6 is a pretty big range. And the stiffness of your leg actually doesn't change over that range. You hit the ground, you come off the ground faster, but it changes the way that you hit the ground at what angle and how you flip over. It doesn't change so much the stiffness of your leg. And so they hypothesized that the reason this was really happening is because you have this great Achilles tendon in your foot. And that Achilles tendon stores and returns energy with every time you hit the ground. And its stiffness really isn't changing so much. It's a material property. You can't change it by activating your muscles. It just has a certain stiffness. The same could be said of the plantar fascia underneath your foot. There's actually a lot of elastic energy storing elements on the bottom of your foot. If you actually calculate the work with every stride that you do for running, 35% of the energy that you do comes from the Achilles tendon, and 17% comes from the plantar fascia. So that means more than 50% of the work with every running stride is not being done by the muscles, but it's just with these springs. These are passive springs that can't change their stiffness. So that's a really good argument for why we think leg stiffness really doesn't change much. You're relying on these types of springs, and there are others in the leg. So I wanted to test this idea, and I originally talked to my students and said, well, we could do a surgery and take somebody's Achilles tendon out and put a different spring in, and they looked at me like I was a little crazy. And I said, okay, well, we can't do that, but maybe we can come up with an alternative. Can we build a robot that does this, and let's change the robot's tendon, and then we can see how it affects the way the robot moves. And to do this, we wanted to do it rather simple. This was actually an undergrad project when it started. And we wanted to simplify running a little bit. And in the literature, what we've learned over the years is that if you want to study this, actually a really good way is just to study this, okay? Because when you stop and think about the mechanics of running forward, I can simplify just running in place, and it's not a whole lot different. It simplifies things, but it's very, very similar. I've still got the aerial phase. I've still got hybrid dynamics. And then instead of shifting weight back and forth, you can just switch it a little bit and just do one leg. And if you do that, it's a little bit simpler, but the mechanics still follow the spring mass dynamics, and you still have the hybrid dynamics. So everything works pretty well. There's a lot of studies that have shown that if you do a study with hopping in place with one leg, the results have always carried over to running. So we wanted to build not a running robot, but a hopping robot. And this is what an undergrad in my lab came up with. So it's got a wooden foot with a little soft cushion. And then we have an Achilles tendon that's a spring. And then we have an artificial pneumatic muscle. It's just a specialized balloon. When you pump air in it, it gets short and fat and works like a muscle. You let the air out, it gets long and skinny. And then this is the shank. This is a beam to keep it from falling over because we wanted to make it simple. And then this is your muscle on the front, your tibialis anterior at the front of the shank. Instead of making it active, we just replaced it with a spring. And so there are the different parts: the beam, the force sensor, elastic dorsiflexor, pneumatic plantarflexor, shank, metal tendon, ankle joint, and foot. And what we needed next was the brain, because a robot's not going to hop without some sort of brain. And the good thing is, from neuroscience, is there's a lot of people that have come up with good equations to actually model how your spinal cord works for locomotion. And you don't have to memorize this. There's no test at the end. But these equations, which are relatively simple in terms of the math, describe these neurons. So here's one neuron, here's another neuron, here's how they interact, all these connections. And we can actually use this to mimic how your own nervous system works during locomotion. So we combined that with our robot and put it together, and this is what we got all of a sudden. This is really cool, because we didn't know if this was going to work, but all of a sudden it just started happening. Because it was taking the sensory information, and it was its natural state. It's something it wanted to do if you turned up the excitement level. That was the key. So in the equations, there's actually a descending command from the brain, and if we made the brain excited, it started happening. If we made the brain not excited, it just stopped. But with this, we were able to go in and change the tendon stiffness. And what we wanted to know is, does the leg stiffness correlate with what the tendon stiffness is? And lo and behold, it does. So the easiest way to measure this was looking at how long it was on the ground, because a stiffer spring actually moves faster, rebounds faster, and a less stiff spring is going to take longer to move. And so to show that point, this is a good time to go over to our demo. And so what I have are 3 different springs here, different stiffnesses, 3 masses, exactly the same mass, okay? These do not have hybrid dynamics because there's no aerial phase. They're just going to move up and down. So if I do that with this spring, you can see it move, okay? Now I'm going to go to a little bit stiffer spring, and you can see that it moves faster, up and down. And if I go to a little bit stiffer spring, it moves even faster. And so the frequency of the motion depends on the stiffness and the mass. Stiffer legs, stiffer springs means you bounce faster, okay? A big difference between these is there's not hybrid dynamics, and so you have an aerial phase which sort of cancels things out. But because of that aerial phase, the easiest way is to look at ground contact. And so that's what we did, is looked at the ground contact, the stance phase here, versus the mechanical resonance. So what would be predicted based on the stiffness and the mass isn't changing. So as we move this direction, we use stiffer springs. And what you find is that the black line is what would be predicted, and all of our data from our hopping robot follows this dashed red line. So it looks like it works pretty well. Is if you change the stiffness of your tendon, which happens, what you find is that people that lift weights get thicker tendons, not just bigger muscles, but thicker tendons, and those tendons get stiffer. And it turns out runners that run a lot also tend to have a little bit stiffer tendons. They it's almost like a hypertrophy because of the running. There's always stretching them, and so the tendon responds to that and actually gets stiffer. So we know there are ways that you can physically change over long durations your tendon stiffness, and it seems like it should predict what's going on. So let's go back to rubberized tracks. When I was at Berkeley, we wanted to know, does this rubberized track change things? Because essentially what you're doing is you're adding a spring in series with your own leg spring. So here's the motion from the heel contact to the middle of the stance phase to taking off. And if you've got a surface that's got a bunch of springs on it and it gives way, then what you end up seeing is that now the dynamics of how this spring mass system move are going to be different based on this surface spring. And so if you don't change your leg stiffness, you're actually going to run differently depending on the surface. If you run on concrete versus asphalt versus one of these rubberized tracks, you're actually going to run a little bit differently. So I talked to my advisor, because she was a Tom McMahon student, into following up on this. In the end, it proved Tom was wrong with his initial papers about predicting how to build the surface, because he didn't have the hybrid dynamics in his model. He didn't have the aerial phase. And he assumed that leg stiffness stayed constant. And we were basically going to test that. So I built a big rubber track in the lab, and this is rubberized material that I could stack. So I could put 3 or 4 or 5 or 6 of them and change the stiffness of the material. And one of the things I learned the hard way was if you recruit different sized people, they have different sized feet. And I didn't think about that until I got all the data and I was looking at it. And it turns out people with big feet compress more springs than people with little feet. So the surface is not the same for everybody. If you've got bigger feet, you compress the surface a lot more than if you have small feet. And so I actually had to make individual lines for each subject for all my data. So when I measured leg stiffness, staying at the same running speed, this was about 3 meters per second, versus a range of surface stiffnesses, so 4 different surfaces I put down. I then have each of these different colors as a different subject. There's 5 subjects, and then I fit the data for all the subjects. And what you see is it's not constant, like Hecrom and McMahon found, is that as you change the surface stiffness, it actually changes. The lower the surface stiffness, the stiffer your leg. These numbers are going up. So what is the outcome of this? And it turns out that even though the surface was compressing more and more as you made it more compliant down here on this end of the scale, that the displacement of their center of mass, the path, if I was running behind here and you couldn't see my feet, the path of my head and my torso was staying exactly the same. So I was changing the stiffness of my leg to accommodate the surface. And in doing so, I felt the same rhythmic motion that I always do. So that was actually a really good way to predict how a surface was going to change, because then you can predict the leg stiffness based on the surface stiffness, because you're expecting that this is not going to change. The center mass displacement stays constant. The byproduct of this is things like the ground reaction force, peak force doesn't change very much at all. Contact time doesn't change. There's a lot of other parameters that fall out of this. So because of the hybrid dynamics, you can assume that leg stiffness stays constant. People do adjust it. They have to use their muscles to do it because their tendons aren't going to change. But you do have muscles, and you can activate the muscles differently and basically keep the same motion pattern, even though you go from a springy surface to a non-springy surface. A far extreme of this, if you've ever seen the gymnastics, is that this floor exercise mat is very springy. So I talked to Bev Plocky, who's the coach of female gymnastics, women's gymnastics, and it was a little hard to bring the whole floor exercise machine in to demonstrate this, but she did say I could borrow one of the springboards. So we have a springboard to try to demonstrate this today. So I would normally ask for a volunteer, but I don't want to hurt anybody. And you actually have to be fairly massive. If you don't have a lot of mass, it's harder. So I think I'm going to demonstrate it myself, and we'll see how well this works. And if it goes well, we may get another subject up here. Springs are great for gymnastics because they want to get extra energy and do flips. They want to spin. They want to get higher. If you're talking about a vault, they run down, build up a lot of kinetic energy, hit the springboard quickly, translate all of that kinetic energy into elastic potential energy in the springs, and use it to get upwards to gravitational potential energy. That's for maximal performance. Springs will definitely help you. There's no doubt about it. But for running and just looking at you run around the everyday place, you're not doing maximal performance. You just want to do it, and you follow the principle of laziness. You choose a pattern that uses the least amount of energy. So what I want to do is do a quick experiment and see how well this works. I'm going to hop in place for 10 hops, and I'm going to do it after I hop for a bit, because if you ask people to just hop in place, they're like, oh yeah, this is great, I can do this. But eventually, what ends up happening is they slow down. Yeah, I lost my mic. So what ends up happening is that eventually they slow down and they just adopt a pattern that works, okay? And they'll do that for a long time. And if I measure how long it takes to do 10 hops, which what we'll do right now, then we're going to compare it to doing 10 hops on the springy surface. Because if I'm adjusting to accommodate the different springs, the amount of time it takes for 10 hops here should be the same as the amount of time for 10 hops there. From that simulation, or that demonstration, what you saw is that if I change the stiffness by adding the springs, it should move at a different rate. But what ends up happening is because I change my muscles differently, you actually get the same time. So we'll do it real quick. You got one? Or can you just hit start and stop?
Okay.
Okay, wait, don't start it until I tell you.
Yep.
I'm going to get just to a nice rhythm, and then 3, 2, 1, start. Stop. Oh, well, we got to do that again.
It did need a lap, so what you want?
Yeah, we'll do it one more time.
Okay.
Start. Stop. Okay. Now we're going to do the same thing over here. So how much time was that?
5.7.
5.7 seconds. Okay. So if I don't change the stiffness of my legs, what it should end up happening is this should actually take a lot longer because now there's extra springs that are giving more compression. And so we'll see how well it works. So I'll get moving. 3, 2, 1, start. Stop.
5.36.
Okay, a little bit off, 5.4, but if you look at the predictions, it should be within a certain time point. That's probably just the error from me not being used to it. But over time, it gets to be the exact same. And so even though gymnasts use these to maximize their performance, if you do it for running on a long duration, you adjust your own mechanics. And so the reason I'm going to tell you this is because we need to come back to this. What is the difference between having no shoes on and having shoes on? And the shoes are essentially little springs on your feet. They basically have a little bit of stiffness to them, a little elasticity, and so they actually change the way you're running. In the early days of running shoes, back when Nike was starting the field, there were a lot of biomechanists in academic labs that were trying to figure out why I put one shoe on you and then I tie another shoe. And I know there are differences in stiffnesses, but there's no difference in ground contact times or ground reaction forces. And it's because they never really expected that the people were adjusting to the shoe. And that's what ends up happening, is whether you're running on compliant surfaces or have shoes on, you tend to adjust to different types of shoes. And so when we look at the data, the one thing that we can say is that if you look at people running in shoes, like the top graph, so this is a vertical ground reaction force, and that's time. So basically that's one phase of ground reaction force between your foot and the ground. Aerial phase is here, and then another step. You see that you have a peak, and then you have this impact peak from your foot slapping the ground. When people tend to run barefoot, they tend not to have those impact peaks. They tend to run on the balls of their feet a little bit more. That's not to say it's better or worse, it's just different. People tend to run on the balls of their feet barefoot, but the peak forces tend to be almost identical, and that's because they adjust the stiffness of their leg. The only thing that changes is this passive foot slap portion. And so when we say, you know, which is better for you, you can look at all the data, but there's no real evidence that one is better than the other. It's not that this loads you any less, it just changes where the load is. This load may end up more on the knees and some of the other joints. This loading is a lot more in the plantar fascia and the Achilles tendon. And so if you're likely to have an Achilles tendon injury or a plantar fascia, you actually don't want to be running like this because you're going to put more stress on them than in this situation. But if you have problems with your knees and your cartilage, then maybe this actually can be possibly not as good as this. But you look at the large clinical studies, there's no evidence one is better than the other. The most clear outcome is if you switch from one to the other and do a lot of miles quickly, you're going to end up injured. So if you're used to running with shoes and all of a sudden you decide to run a marathon without shoes, yeah, you're probably going to get injured. You need to ease into it, give your tissues a chance to respond. Okay, so let's go back to this spring mass model and talk about this guy, Phillips. Phillips was an undergraduate at Arizona State University in the 1970s. And he was out on spring break and had a water skiing accident that cost him his leg. He was an architecture, art, and design, I can't remember which, major at Arizona State. He went to the clinicians and they said, here's your wooden leg. Back then it was not a whole lot different than a peg leg. I mean, it looked a little more like a human leg, but it was a wooden leg. And it really didn't do much. And he was a very active guy. He didn't like that. He decided he was going to move. He was going to go to Northwestern and major in biomedical engineering. And he knew about Tom McMahon's papers and what they were saying about springiness. And eventually, in 1984, he got around to starting to sell his own prosthesis for active amputees. And that's what this active prosthesis looks like. It's a big carbon fiber spring. In the same way that we can use a spring to model human running, you can actually use a big spring to replace what your leg does during running. They're actually not so good for walking or for standing still because we change the dynamics for running compared to other motions and tasks. But if you're going to run, you end up using something that looks a lot like this. It's now called the Oser Cheetah. And the reason it's called the Cheetah is because when Phillips was, when Phillips was looking at the design of biological animals, he said, you know, if you look at the way this cheetah runs, which is obviously very fast, and I want to run fast, why not design it like this? And so that's what this design of this carbon fiber spring came from. Eventually, Oser, which is a big prosthetics company, bought him out, and so they market it as the Cheetah. Many of you may have seen this device as the device that Oscar Pistorius wears when he runs. These are artificial legs, big carbon fiber springs, and he is remarkably fast. If you look at his best times at 100 meters, 200 meters, and 400 meters, these are way beyond any speeds that would have been expected, 15, 20 years ago before Phillips had built the devices. And in fact, in the London 2012 Olympics, he ran in the 400 meters against able-bodied individuals, and he was one of the 16 fastest in the world. He made the semifinals for the men's 400 meters. So that means there was only 15 people potentially faster than him in the world at 400 meters, even though he had no legs. And this came about, actually, he started running. He's had no legs since he was a child. They did an amputation due to congenital defects. But when he started getting good in the 2010 area, the IAAF banned him because they said these legs were making him too fast. Clearly, he had an advantage over able-bodied runners. And so they set up a sort of scam setup at biomechanical measurement where they hired a German biomechanist to do measurements on him to look at very specific things that they wanted to know and nothing else. They made the measurements, then they said, oh, you have a disadvantage. I mean, you have an advantage over able-bodied, so you can't run. And so he went to Roger Crom, who was one of Tom McMahon's students, and a number of other people, Hugh Herr, which was one of Tom McMahon's students. And they did a bunch of biomechanical tests in Houston at Rice University to try to get behind whether or not these actually give you an advantage over being able-bodied. And this is a video of some of their data collections. So again, you'll notice the high-speed video it's got mascot that's collecting its oxygen consumption, its carbon dioxide production. And they're going to look at this running pattern and make two different speeds. And this is what it looks like. You can see the markers on his prosthesis so that they can calculate how much the prosthesis is compressing. And then they have markers on him so that they can record his motion of his leg. And the take-home message from this is that they took all their data, went to the International Court for the Arbitration of Sport, and Roger and Hugh Herr, two former Tom McMahon students, made the case he really doesn't have an advantage. And the court sided with him, and he was allowed to run for the Olympics. It does not look like he will be running anytime soon, but that's another story that I'm not going to get into today. But if you look at the data, one of the biggest arguments that they made of why we think that he doesn't get an advantage is if you look at his ground reaction force pattern. This is the vertical ground reaction. This is a horizontal. Mainly I want you to focus on this. These are non-amputee sprinters running, and this is Pistorius. And what you see is there's a huge difference in the amount of force that you can push off against the ground. And Pistorius, because of his prosthesis, he can't push even harder. He doesn't have muscles to push against the ground. He's just got to bounce off the ground. So it turns out he does have a limitation in that he can't push harder because he doesn't have the musculature to produce more power and to hit against the ground even harder. So this brings up, well, why do people run so fast? I mean, if we look at somebody like Usain Bolt, who's very big, he seems like he's one of the fastest in the world. What is it about the dynamics of running that we can make predictions that will make you run faster? And I'm not talking about faster over a marathon. I'm talking about faster for 100 meters or 40 yards or whatever it is that you want to do. And we can go to our spring mass model and actually make predictions. So Tom McMahon did this in his 1990 paper. And he showed that if you keep mass constant, one way to bounce off the ground faster is exactly what I showed you over in the demo, which is if you go to a stiffer spring, you rebound off the ground faster. People choose not to do that over normal aerobic long-distance running speeds, but do they do it at fast running speeds? And it turns out sprinters actually do increase the stiffness as they get to faster and faster speeds. This model would predict that you make your legs stiffer, you're going to run faster. And we also have Mark Rabert, who did some really cool robots in the 1980s that basically followed spring mass model. So Mark Rabert was at MIT at the time. He knew Tom McMahon. He knew of the spring mass model. He was building robots that were essentially spring mass models. This is a big mass on a single pogo stick. And that pogo stick has a little actuator that adds more air so that it gets thrust, because it's not a perfect pogo stick that doesn't lose any energy. It loses energy. And then he built a lot of other hopping and running robots that follow the same spring mass dynamics. And he actually had one undergraduate in the lab for a senior thesis that did exactly the experiment, which is what happens to the way the robot can run if I increase the stiffness of the leg. And so he collected the maximal running speed and he kept changing out the spring stiffness. And it turns out the stiffer the spring in the leg, the faster it would run. So again, not only do we have the model predicting it, not only is there data from humans showing you that human sprinters make their legs stiffer at the high end, but that we also have robots that can do this as well. Okay, I'm almost done, but I know there was one thing that you were really hoping to get out of this meeting, this session, and that is if you come across a Tyrannosaurus Rex, what do? It comes up every time I'm meeting somebody at a coffee table or something. They've seen Jurassic Park, and if you watch Jurassic Park, they say, stand still, don't move, because of the vision of the T-Rex won't allow it to perceive non-motion. I can't verify if that's true. I don't work on the visual system of T-Rex. But in this movie, Jurassic Park, the T-Rex chases a Jeep at 30 miles an hour. And the good thing going is that as a biomechanist, we can actually evaluate how fast could a T-Rex run. And I've got a buddy, John Hutchinson, who did his PhD at Berkeley too, that spent his whole dissertation, most of his dissertation, looking at things like that. And he did biomechanical modeling of T-Rexes. And he did it with different levels of complexity. And the take-home message that I'm going to leave you with is that you can most likely outrun a T-Rex. If you're in good shape and you run on a regular basis, take your chances and run from the T-Rex. If, on the other hand, You are not a runner. You don't regularly run. Go with the Jurassic Park method and stand still. If it works, let me know. Text me. I'll give you my phone number. But if you model it, the reason T-Rexes couldn't have been so fast is that they suffer from the problem of getting bigger. And being bigger means that your mass and your weight increases as a function of your leg length cubed. Because we're talking about volume of a sphere or volume, let's say volume of a cube. So if I make that cube bigger, the mass and the volume increased with whatever length you want to measure cubed, because it's three-dimensional. The strength of your muscles and your bones increases with those lengths squared. The bigger the muscle cross-section is, the stronger the muscle is. The bigger the cross-section of the bone, the stronger the bone is. So as you get bigger and bigger, you end up with a problem that you are less strong relative to your weight. This is why when you look at, one of the reasons why the best gymnasts and the male gymnasts and female tend to be small. They are strong for their weight. They're powerful for their weight. If you go to Olympic weightlifting and you look at how much the weightlifters lift, the biggest weightlifters lift the most, but if you normalize to their body weight, the smallest ones are the ones that lift the most weight because they have the advantage that they're stronger relative to their body mass. That's why ants can lift 200 times their body mass. It scales to your benefit as you go smaller. When you scale bigger to T-Rexes, you can't handle the forces that would come along with running. Okay, so take-home messages besides the T-Rex. Remember that we all run like springs. We have hybrid dynamics. We have one set of equations that dictate what happens in the air, like projectile motion, and another set that dictate what happens when we are on the ground. When you put shoes on versus non-shoes, your leg's going to adjust those shoes anyway. You will redistribute the stresses in different places. There's no real evidence that one's better than the other, but whatever you do, don't jump into a new running style immediately because it takes time to build up the strength. And if you want more springs on your feet, there are these devices out there, power skips, and there's others, that are essentially big pogo sticks that you can put on your feet while you run. I love the Muzak in the background. I actually don't get any money if you buy these, but they show, again, so for maximal performance, you can store up that energy. So this is just like a mini tramp that you can get extra energy out of. Do they make you use less energy to run? And the answer is actually no. And the reason is you're adding a whole lot of mass to your feet. And it's like putting big ankle weights on. So it's kind of fun that you can store energy and get more back, but because you have to swing your legs during the aerial phase and have these extra weights, and it's actually a pretty big workout. Your hip muscles are going to feel a little sore the day after you first try these. So I'm going to end right there. I want to say thank you for listening. I also want to say thank you to Bev Plotke, University of Michigan Gymnastics, for loaning me the springboard. If you would like to come up afterwards when we get done and try out the springboard, you can as long as you're safe, please. And I'd be happy to take any questions.